Alright, this is just a quick video on probably one of the easier things to do with vectors. It's called the dot product, and if you have a vector u which has components u1, u2, if you like the ij notation, this would be u1 I hat plus u2 j hat. And the same thing for v, we have v1, v2. Then if we dot product these together, now this is not multiplication, um, because when you take a vector and you multiply by another vector, there's really no definition for that. So they change this, and this literally just becomes read as dot. So when you do u dot v, the definition is the product of their first components, so u1 times v1, and then you add on the multiplication of their second components, u2 and v2. So it's actually kind of easy. So if I gave some vectors, just some simple ones, vector -2, 3 for u, and v equals -4, -7, then if we want to do the dot product between these two vectors, we're going to get the product of their first components, so -2 times -4, plus the product of their second components, 3 and -7. Not many people have a problem with dot products. They're pretty simplistic, but their interpretation is a little interesting. So here we have +8 minus 21, so u dot v is going to equal -13. So before this, there was the sum of vectors and the difference of vectors and scalar multiplication of vectors, and each one of those, their operations generated a vector. But in this case, when you do a dot product, what you're generating is a scalar. So the dot product between two vectors is an operation on two vectors that generates something that is not a vector. It's a little strange, but it kind of works out in the end. Alright, so the dot product of two vectors is a scalar. The dot product actually has a few properties which makes it a unique system. Kind of like the real number system has its own little properties. Sometimes these dot products have shared properties with the real numbers. Alright, so here's the definition of the dot product. Here we have two vectors, and one thing I have to prove is how do component vectors work with constants, and I don't remember if I've done this earlier. So let's look at the constant c, scalar multiple c, times the vector u in components. And there is no distribution here because components are a little strange, and this is a real number out here. So what I have to do is kind of prove that the distributive property actually kind of works. So I'm going to rewrite this as u1i hat plus u2j hat. And that way, what we have here is an algebraic expression with a constant sitting out front. And now the distributive property can kick in. So we're going to get c times the first one plus c times the second one. Distributive property of real numbers. But then we can rewrite this as a component as cu1 comma cu2. So therefore, I have just proved that the distributive property works over component vectors. Alright, the only proof I want to show you is the distributive property of the dot product. So here we have u dot v plus this other vector w, of course, is going to have components w1, w2. So if I do this, the only thing I can do is write them as components. So u is u1, u2. And we're going to dot product that with v1, v2. And we're going to add on to that one w1, w2. Okay. So I can add inside first, parentheses come before multiplication. So this becomes u1, u2, dotted with the sum of these vectors, which would be, oops, v1 plus w1 comma v2 plus w2. When you're adding vectors, you just add their components. And now we can perform the dot product because this is a vector dotted with a vector. So we're going to get the first component of the first vector times the first component of the second vector. And then we're going to add on the second component of the first vector, u2, times the second component of the second vector, v2, w2, added together. And now this is all real numbers. After you're done with the dot product, everything turns into scalars. So all the scalar properties are going to work. Distribution. So we're going to get u1 v1 plus u1 w1 plus u2 v2 plus u2 w2. Oops. Now, what I'm going to be looking for is commonalities. For instance, here's u1 v1 and here's u2 v2. When you look at them together, they become u dot v, because that's exactly what u dot v is equal to. Alright, similarly, we have u1 w1 and u2 w2. Well, that's going to be plus u vector dotted with w vector. That's the pure definition of it. So we have here that u dotted with v plus w actually distributes. You get u dot v plus u dot w. This just allows you to do it, add the vectors first and then dot them, or dot them individually and take their answers and add them together. It's a nice little property.